Welcome to my presentation on an efficient solution for one-to-many multimodal journey planning. My name is Jonas Sauer and this is joint work with Dorothea Wagner and Tobias Zündorf. In this talk we will be focusing on multimodal journey planning. So we are given a public transit network which consists of trains, buses, ferries and other types of schedule-based transportation. And additionally we allow one secondary transfer mode such as walking or biking. So far, the state-of-the-art in multimodal journey planning has only focused on one-to-one queries. So we are given a single source location A and a single target location B, and we are interested in the best journeys between these two locations. A related problem setting is the one-to-many setting, where we still have a fixed source location but several target locations, or in the most extreme case, the one-to-all problem, where we are interested in journeys to all possible target locations in the network. There are some interesting applications for this type of problem. For example, if you consider the graphic in the top right, what you see here in the center is JFK Airport in New York, and the highlighted areas show the areas of the network which you can reach in 30 minutes, 60 minutes and 90 minutes respectively from the airport. These areas are called isochrones, and computing them obviously is a type of one-to-many problem. Another applications are point of interest queries, such as given my source location, what are the k nearest supermarkets? And finally, in road networks and public transit networks, one-to-many queries are often a component in pre-processing techniques which are used to solve queries faster, and potentially this could also be used in a multimodal setting. Now let's formalize our problem statement. We are given a public transit network which consists of a set of stops representing bus stops or stations and a timetable which defines how the vehicles move through the network. Our secondary transfer mode is represented by a transfer graph consisting of vertices, edges, and transfer times for each edge, which might represent walking, for example. We combine the network and the graph into a multimodal network, and now we are given a source vertex S, a set of targets T, which here are represented by the shop icons, and a departure time, in this case 11:32. And now our objective is to find for each target in the target set a journey from S with minimal arrival time, which in this example might be these four. Now let's recap some related work which we will be building on in the following. Contraction hierarchies are a well-known speed-up technique for one-to-one searches in road networks, and what it does is it iteratively contracts vertices and inserts shortcuts between its neighbors to preserve shortest path distances. So if we contract this vertex, we have to insert a shortcut between its two neighbors, and then we contract another vertex, and another one, and progressively we create a hierarchy of vertices and shortcuts between them based on the order in which we contracted the vertices. And now we can perform a query between S and T by performing an upward search from S, which only follows edges to vertices that are higher up in the hierarchy, and the same from T on the reverse graph, and we obtain an up-down path that represents the shortest path from S to T. There's also a one-to-many variant of this algorithm, which is called bucket CH, which will appear a few times in the rest of the talk. Another technique that we adapt is Ultra, which is a speed-up technique for multimodal one-to-one queries. What it does is it pre-computes shortcuts that represent transfers between two vehicles. And then in addition to that, we also have transfers from S to the first vehicle and from the last vehicle to T, and we compute these with two bucket CH searches from S and T. Once we have that information, we can disregard the original transfer graph and simply route on this input using any public transit algorithm we like, and this creates a multimodal version of that algorithm. Now the problem with Ultra, if we want to use it in a one-to-many context, is that the exploration of initial and final transfers is inherently bidirectional because we have to perform a backward search from the target vertex T, and if we have multiple target vertices, this is no longer feasible. Another one-to-all technique that we build on is called FAST, which starts with an upward CH search from the source vertex, as in the CH query, and then we need to find distances to all vertices in the network. And what we do is we store the vertices in a topological order regarding our contraction order, and then we can simply sweep over the vertices in this order. And what we do for each vertex is that we relax its incoming downward edges to find the correct distance to this vertex. If we have a set of target vertices in a one-to-many setting, we can adapt this approach by performing a target selection. So what we do is we identify all vertices in the downward graph which we need to visit in order to find the distances to our targets, and we disregard all the other vertices, and then we simply sweep over the remaining vertices. Now I want to show you our contribution, which is to adapt ultra to a one-to-many setting by adapting ideas taken from FAST. So we now have a source vertex and a set of target vertices as before, and we also have a public transit network in there. So what we do in phase 1 is we have to compute initial transfers from S to the public transit network. We do this with an rFast search to the set of stops. So we have our upward search and then a downward search on the target selected graph. The reason we don't use a bucket CH search as we would do in Ultra is that in this case where we have multiple target vertices, no target pruning is possible. So in this case, rFast is actually faster than bucket CH. The second step is to perform a public transit query. We do this as we would in Ultra, using our Ultra shortcuts, and we obtain distances to all stops in the network. So we can disregard the public transit network for now and imagine that we simply have inserted dummy edges to each stop in the network labeled with the correct distance. And now the crucial part is step 3, the final transfers to the set of targets. At first we might think that this would be a many-to-many search, so we would have to compute distances from each stop to each target, which would be quite expensive. But in fact, this is only a modified version of one-to-many search, because in the end we are interested in distances from the source vertex to each target vertex, and this path from the source vertex to one target vertex always runs over exactly one stop, and we only need the distance from this stop to the target vertex. The only problem is that we do not know which stop this will be in advance. So what we can do is we can insert dummy shortcuts to our stops, which are labeled with the distances that we obtained after the public transit search, and now we could perform an rFast search where we add these shortcuts to the upward search and then perform an upward search from S followed by a downward sweep to the targets. The problem with this is that we will reach all stops in the network, and therefore the upward search will visit every vertex in the combined upward search space of all stops, which will be the entire area highlighted in red. So what we can do, which is more efficient, is to instead perform an upward sweep from the set of stops, which is analogous to the downward sweep we perform to the targets. So we have an upward sweep here, and then we perform a downward sweep to the set of targets. And this is our query. Now let me give you a quick overview over the algorithm in full. In the first phase, we perform an rFast search to the stops for the initial transfers, which obviously has the cost of one rFast search to the set of stops. Then the second step is the public transit query, which we can perform with any public transit algorithm using ultra shortcuts. And in the third step, we have an upward sweep from the set of stops, which is approximately as expensive as an rFast search to the set of stops, and then a downward sweep to the set of targets. So in total, the cost of our algorithm is one public transit query, two rFast searches to the set of stops, and one rFast search to the set of targets. We evaluated our approach on the public transit networks of Switzerland, which was taken from a public GTFS feed, and Germany, which was kindly provided to us by Deutsche Bahn. The timetables comprise 2 successive days, and we combined them with transfer graphs taken from OpenStreetMap, using walking as the transfer mode with a speed of 4.5 kilometers per hour. As the basic public transit algorithm used in our query, we used connection scan algorithm, which is the fastest known algorithm optimizing only arrival time. We had to create our own baseline algorithm, as there was no previous one-to-many multimodal algorithm, and we did this by using MCSA, which is an existing one-to-one algorithm, and adapting it to one-to-many search in a straightforward manner. And then we have our approach, which we call UPCSA, which is the combination of ultra-fast and CSA. Before I show you the results, I want to show you how we chose the target sets for our queries. The query performance depends mainly on 2 things: the number of targets overall and the distribution of the target set in the graph. The further the targets are apart, the larger our target selected graph used for the sweep will become. To capture this, we used ball target sets using as input a ball size B and a number of targets T. And what we did was we picked a random center vertex C and then grew a ball of size B around it containing the B nearest neighbors of C. And then inside that ball we picked T targets at random. And so the ball size controls the density of the targets in the graph. So here we have a plot showing the performance of our 2 algorithms depending on the target set size and the ball size. The 3 lines up here show the performance of the MCSA algorithm, and the different lines are for different ratios of ball size to target set size. The reason some of these lines end prematurely is because in these cases the ball started to outgrow the size of the graph. What we observe for the MCSA algorithm is that fairly quickly the running time for the graph exploration starts to dominate the overall running time. Whereas down here for the UPCSA algorithm, it stays fairly similar, and the running time for the public transit network dominates the running time. So our UPCSA algorithm scales much better. Now I want to show you some detailed running times, first for the Switzerland network, for 3 types of target sets. First we have the one-to-all search, where all vertices are targets. Then we have the set of stops as the target set, and finally a ball configuration of moderate size. We perform 10,000 random queries for each type of target set. For the one-to-all search, we observe that our approach beats the MCSA approach by about a factor of 7. We see large reductions in the running time in both the initialization phase and the scanning phase, and overall the transfer exploration in these 3 phases takes up about a third of the running time. For the stop and ball configurations, we see that the running time is dominated by the scanning phase, which is about 90% of the running time for the stop configuration, and the total running time is about a factor of 2 smaller than for MCSA. We observe similar results on the Germany network. We have a reduction of about a factor of 7 for the vertex set and a factor of about 2 for the stop and ball sets. In summary, we adapted Ultra to one-to-all and one-to-many scenarios by incorporating ideas from RFast. For moderate target sets, we managed to reduce the transfer exploration to only about 10% of the running time. For large target sets, we achieved a speed up of up to 7. There were some aspects that I didn't have the time to go into, namely delaying the contraction of stops and targets during the CH computation can significantly reduce the size of the stop and target selected graph on which we do the sweeping. Furthermore, we implemented a variant of our approach that includes Pareto optimization, so we aren't only interested in the arrival time but also the number of transfers. As for future work, we would like to adapt our approach to the applications I mentioned in the beginning, namely isochrones and point of interest queries, and it may also be useful as an ingredient in a multimodal speedup technique that has yet to be developed. So that concludes my presentation. Thank you very much for your attention.